Morning. Am I audible to you guys? Okay, let me share my screen first. So in last class, we mainly discussed about alpha beta pruning. We also check one example, how we can cut off one part of a game tree part with the help of alpha beta pruning. So normally to play game, we use Minimax algorithm, but only problem with Minimax algorithm was that you have to check for each and every node in your game tree. But in practical cases, it's not always very convenient because we have limited amount of time, right? So with the help of alpha beta pruning, we can just prune some part of our game tree. So for alpha beta pruning, we had just two parameters, alpha, which is mainly for your max values, and beta will always select the lowest value, and this is the choice for your mean nodes. Okay, so initial value of alpha will be minus infinity, and for beta it will be plus infinity. Then this was the algorithm for alpha beta pruning. I hope you guys could write this one last time. Then the condition to prune some part was that when alpha was greater than equal to beta. So other points to remember was that the node values will be always passed to your upper nodes, and alpha beta values are only passed to the child nodes. Okay, so whenever we will update node values, we will always take care of these things when we apply alpha beta pruning. So this was the example with the normal one, and this one was with alpha beta pruning. So I give you guys a task to do at home. Kunba Korisila? Have any one of you just tried this one? Forgot. আচ্ছা ঠিক আছে. You can update me now, and then if you have any confusion, you can tell also. So this was the game tree I provided. So first turn will be always max's turn, then mean, then max, then these are our terminal nodes. So for the terminal nodes, we always have utility functions, and for the internal nodes, that means non-terminal nodes, we have minimax values, and we need to calculate that minimax value from the utility values. Okay, so from max here, we don't know the node value yet. So you can just initialize it as minus infinity. Then alpha beta value also we don't know yet. So for alpha it's minus infinity, and beta is also infinity. So same value will be passed to this node first and then this node first, because it's a DFS, depth first search. So it will always start from the left hand side, right? So at this node, what happened? First node, first child node for this max node is 2, right? So our node value will become 2. Okay. Now Since node value is 2 and it is max's term, so our alpha value will be updated to. Okay, so this value will become 2. Okay, next I have, for this node, I have another child node which is 3. Okay, so from 2 and 3, which one is the highest value? 3, right? So, and it's a max, so it will select this value. So, this value will be updated as 3 and this alpha value will be also updated as 3. Okay, so the node value here is 3, correct? So, this same value will be propagated to your previous node. Okay, so now node value I can update it as 3. Now when you update it, see it's a mean mean node. Okay, that means the changes will happen only the beta value since it's a mean node. So this beta value will be updated to 3. Okay, next for this particular mean node we have another branch. So this value will be passed down here. So for this node, we exactly don't know the V value yet. Alpha remains same and beta value equal to 3. Okay. So for this node again, we found 5 first. So I can say V value equal to 5 and I'll update it as 5. Okay. Now you can see at this point your alpha value equal to 5 and beta value equal to 3. So now it is satisfying the condition that alpha is greater than equal to beta, correct? So I will simply prune down this part. I'm not going to go to this part and check whether what type of values are there. Okay, because here max value is 3 for this node, value is 3, and for this node I found value is 5. So obviously next case is the mean node, right? So no matter what value it is, we are not going to consider it, correct? Because we have already found that there is a value which is 3. And it is also satisfying the condition that alpha is greater than 3. So there is no point to waste the time by searching for this node, because for this node it can be maybe more than 5 or it can be less than by 5, but still since it means we got 3 here. And the condition is don't waste time, alpha greater than b, just prove. Okay, so here the node value become your 5. Okay, so this value will be propagated here again. Okay, now you see the node value for this particular node is 3 and here I have 5, correct? But it's a mean value. So I'm not going to update it because it's already taking a smaller value. So V will remain 3 and everything will remain same. Okay. So next, here I will propagate this value to your max node. So when I will pass this value, this node value will become 3 here. Okay. So since it's a max value, the only updated value will be your 3. Okay. Since it's a max value, here I updated node value 3. So for max node, only alpha has been updated to 3. Okay. Beta will remain same. We don't know the beta value yet. So it's just plus infinity. Okay. And this value will be passed down here. Now again for this node, we don't know the values yet. But when you pass down to the child node, only the alpha beta values are passed, right? So alpha value will be passed and this will remain same, and same process for this node also. We don't know the value yet, alpha and beta. Alpha value is 3. Okay, so at this node, first I found 0. Okay, so I will update the node value as 0. That's a max node. The value is 3 and I just found 0, but 3 is higher than 0. Okay, so I'm not going to update this alpha value because it's just a small value. So, but I just updated the node value, not alpha value. Okay, now again for this node, there is another node which is 1. Now from 0 and 1, 1 is the highest, so I'll take node value 1. Okay, again I am not going to update the alpha value because 3 is greater than 1, right? So I will not update the value. So this value will be passed to the upper node. So node value will become 1 for the time being. Node value will become 1 here. Okay. Now from here you will only update the beta value. Why? Because it's a mean node. So for this node value 1, you will update the beta value 1, right? So now at this point, again, it is satisfying the condition alpha greater than beta, 3 is greater than 1. So I'm going to prune down this part. I'm not going to follow this part at all. Okay. So same value will be again updated here, but now it's a max node. So here node value was 3 and here node value was 1. It's a max node. It will only select the maximum value. But it's already 3, so I'm not going to change anything because it has already taken the maximum value of among these two, between these two nodes. So this is your optimal path with the help of your minimax value with alpha beta pruning. So even if you don't, the whole process is exactly same like minimax, only point is the alpha beta parameter, and you can see that it is just like your minimax value. So even if you don't do not complete the whole search tree of the game tree, still you can get the exact answer. You can find the optimal path. Okay, so if you want to write down this part, kiba buja nai jodi koba. If any confusion, just let me know. Okay. Clear, no doubt. বুজি পাইছা? Complete whole কৰা. Is it clear now? Okay. Okay. Clear. Okay. লিখা হ'ল. Could you just follow it? Done writing? If you are writing. Yeah. Okay. These things are mainly for your two-player games, right? But what happens for your minimax algorithm, you need to generate your entire game search space, right? Again, even if you use alpha beta algorithms, it will allow you to prune large part of it, but still you have to just go all the way to the terminal states, at least for one portion of the tree, right? But this step is not usually very practical, okay? Because in real time, maybe we have a few minutes, okay? So for the real time value, Shannon was a programmer that time who provided a program for chess playing. Now you can see chess is also a two-player game, but there are lots of things involved in chess. It's not like just two moves. There are lots of characters. You have pawn, bishop, then queen, and all. So lots of things are involved. Factors are involved in case of chess. So for that type of game, he provided a different kind of thing. So he idea proposed an evaluation function concept. So what is evaluation function? He just proposed that we can just cut off the whole search earlier by simply applying a heuristic evaluation function. So this evaluation function is basically your heuristic function, and it is similar type of heuristic, a bit similar, not exactly same, like we discussed in the previous chapters, right? So he said we can just update your minimax or alpha beta pruning in two ways. We can update alpha beta pruning, or you can say minimax, by replacing the utility function with a heuristic evaluation function. So you can say instead of utility function, we can use a heuristic evaluation. Okay, then instead of a terminal test, we can use a cutoff test. So cutoff test will decide when to apply your evaluation function. An evaluation function will provide you an estimate of the position's utility. Okay, this is mainly for your chess. So evaluation function will just provide you the estimation of the positions of various players, means all those pawns, bishops and all. Okay, so your evaluation function will simply return an estimate of the expected utility of the game from a given position. Okay, so what type of evaluation functions we can use here? Okay, the evaluation functions can be utilized in various ways. For in case of chess, remember we have different moves, like we have pawns, we have knight, we have bishops, we have queen and all. So we can say that we can calculate these various features of the state. Okay, various features means, by features I'm telling you the types of players like pawns, bishops, and knight. Okay, and we can just provide some values there. Okay, we can just provide it expected value. In normal way, how people just guess it means, suppose two players are going, then you just go to their place, then you will see the position of those players, means those pawns and all. So based on the position of all those players in the board, you can decide maybe this person has like 80% chance of winning, maybe there is a 20% chance of loss, or maybe there are just 8% chance of draw game, right? So these are your expected values, but computer programs cannot exactly find that expected value, so it just provides some material values. Okay, so material values means, maybe you can say for a pawn you have value 1, then for knight or bishop you might have value 3, then for the rook maybe the value is 5, and for queen you have value 9. Okay, now you can calculate the evaluation function like with this form. Okay, and let's write it, evaluation function for a particular state, w1 f1 plus w2 f2 wn fn. Okay, this part I can just write as summation of wi for a particular state, and I will become 1 and n. So here, what is w mean? W, I can say, is just weight of the value or the pieces. So W can be your weight. You can say value of the pieces. Like your these values 3, 5, 9. These are the values, and F is equal to feature. That is your number of pieces on board. Like you suppose in your board you have 5 pawns, 2 bishops, maybe just like that, just for example. So you can calculate this evaluation function with the weight, this weight like 394 like that, and the number of features means how many pieces are there in your board. Okay. Next, this is how you can just typically calculate your evaluation function, but there are lots of other problems. It means this can be a simplest way to calculate the evaluation function. But again, sometimes it's not just enough. Okay. Again, let's just check what is cutoff function. Okay. Cutoff function decides when you will just stop the search and you will apply your evaluation function. So for the cutoff test, you will just select a def first. Remember, in alpha beta pruning, you just need to go to the all the way down to the terminal nodes. For cutoff test, what it does, it basically sets a def limit. Okay, it just set a def limit, and with that chosen def, whatever move will be selected, the evaluation function will be used there only. Okay, so cutoff test applies that evaluation function at that given def limit. Okay, so you can see if you want to select a depth every time, that means your iterative depending search is more useful, right? In iterative depending search, we basically set a depth first. If we don't find something, then we again increase the depth, and then if still we don't find, then again we increase the depth. So same thing we can apply here as well. So with the help of iterative depending search, we can increase the depth one by one if we, within the limited depth. So first we will select just a depth, which will be like more practical for the games. Means if you have like few minutes, suppose 1 minute, so I can set that it's like, okay, within 1 minute, I should be able to go to up to this depth. So I can set the def limit as maybe up to 5 level. Okay, then I will start doing the same thing, calculate the evaluation function. So at that point, whatever evaluation value I found for that particular node, it might not be like terminal node, it can be even non-terminal node. Still, I'll just stop it there. Okay, I'll stop it there and calculate the evaluation function, and whatever value I'll get, I'll just guess it that, okay, the chances of winning this player will be using this platform. Okay, so that's how uh, you can use iterative depending, because it is more robust approach. Okay, so when time runs out, the program will just return the move selected by your deepest completed search. Okay, but again, there are some practical issues I can show you. Wait now. What can be the practical issues here? Okay, can you see this board? Can you see this chess board? Okay, so here you can see it's a bit slightly different chess position. So here in A position, what's happening? The black has an advantage of it like two knights and some two pawns, right? So it should win the game. So suppose you set your depth to this level, okay? Then you are saying, okay, black will win, okay? But see, in the next move itself, just for one move, the black will lose after this white will capture the queen, right? But you didn't set your depth limit up to this level. Okay, so these are some practical issues. Okay, so this is also called your, that means sometimes we also need to make our search quiescent. Quiescent means Means we have to consider only those type of states where it might not go wild later. By the meaning while I'm saying like it might not means drastic change in your current state. So we need to also find question search. So it will make sure that any state should not exhibit this wild swings in your values in the near future. Like in this example, we can see if I set a def up to a level where up to maybe this level, and I can say that black is winning, but in the very next step, it just with one move, white is winning, right? So there are lots of factors involved here. Then again, there's another thing called horizontal effect. Horizontal effect means no matter what you do, means there will be a serious damage and it will be like unavoidable. I can give you another example of horizon effect. Just wait. Let me find it. Okay, I got an image, just that there might be a copyright issues here if I directly use it. Just wait. Okay, then. Okay, can you see this board now? Can you see this board? Okay, so here you can, okay, it's going to finish in 5 minutes. I just finished. So here you can see that maybe the black part is winning. The picture is not that very clear, but it's okay. So you can say the black side is winning the game, but here this particular white pawn, it just move one step, then it will become a queen, right? So so this is like unavoidable and it is going to be a serious damage for the black part. Okay. So if you just put a fixed step search, it can just think that I can just avoid the queening move, right? Because just in one step, this pawn will become a queen. Okay. So these are your unavoidable things. So yeah, that time it was not that possible to avoid these things. And just a minute. Hello. Okay. So this is your the problem with the fixed step thing. Okay. Even there are lots of things available at that time, still these are certain problems, and these problems are later means overcome with the help of machine learning things. Okay. So that's all for your evaluation function thing and cutoff functions. Then you can say there are certain games which have a luck factor or chance factor when there is a dice involved. Okay, I'm just giving a little review. So for those games which have like chance factors involved, so your everything will be like minimax algorithm, just that there will be an extra chance node. Maybe if this is a max, then there will be a chance node here. Then again, maybe it will be mean turn. Then again, for mean also, there will be some chance nodes where your dice will be involved. Okay. I will not explain about this type of games. Just remember that all the games where any chance are involved, like your dice, Ludo and all. So for that type of game, there's a chance node when you draw the whole tree. Okay. That's all about in your adversarial search. Okay, these are mainly your two-player game. You just want to say if it's a multiplayer game. So instead of just storing one value, if it's a three-player game, okay, not this one, then it will just keep a vector of values. Suppose three players, then a vector will be stored in your terminal nodes as the utility function, and if it's the move for A, this one will be B and this one will be C. Okay, so for each node there will be chances of the other node. Maybe if this is the move for A, then there will be turn for B, and there will be also turn for C. Okay, this will be C's turn. Then there will be your terminal nodes like other one. Just that in the terminal nodes, you are going to store the vector of values A, B, and C. Okay. Then again, maybe 4, 2, 3, then 6, 1, 2, and all. Okay. Similarly, you will just put vector of values, then same values will be passed to your upper node. If it's a turn of C, the value for 6 and 3, 6 is higher, so C will select this vector of values. Okay, the rest of the process is just same, just that you need to see which turn is this. So accordingly, it will select the min, max and all. So all the players will try to find the maximum value for that particular one. Right? So concept is same like minimax, just that if it is multiplayer game, then it will be a more values stored in the form of a